For those of you joining us online, you can feel free to type questions in if you don't want to talk, but you're also welcome to talk. We would love to have you talk. Let's go ahead and begin. We are not going to have time to necessarily go over everything, but we will go through, I'd like to go through especially those things which you particularly have questions on. So if there's something that you're like, I really don't need to worry about this particular section, we can just skip that. So, are there any questions that you'd like me to start with?
Me too.
Number 2? Sure. Okay, so number 2. It says, which one of the following exhibits dipole-dipole attraction between the molecules? So this one's tricky because you have to basically identify which one of them is polar. Now, some of them are obvious, like you can rule them out, okay? Like Cl2, that's an obvious nonpolar molecule, right? There's no way to have 2 atoms bonded together and they're the same atom and have it be polar, right? Now, others, the rest of these, you're probably going to have to do Lewis structures for. Now, for BCl3, boron is an exception to the octet rule. I'm going to go through this. Boron, BCl3, how many valence electrons does boron have?
6.
You'll need your periodic table. It has 5 total electrons. How many valence electrons does it have?
4.
3. Remember, the valence electrons are the outermost S and P electrons, right? So the column it's in the periodic table, that also tells you the number of electrons, number of valence electrons. And it's in column 3A, so that's 3 valence electrons. Now, chlorine has how many valence electrons? 7. And there are 3 chlorines, so it's going to be 3 times 7 plus 3 is going to give you 21, or 24 rather. 21 plus 3. Now, when I draw my skeleton structure, I just show how the atoms are connected. BCl3, by listing the B first, it's saying that boron is connected to 3 chlorines. So, in this case, I will draw boron connected to 3 chlorines. Now, that's already used up 6 electrons because each bond is a shared pair, right? And that gives you 18 valence electrons. So I have 18 remaining. I place my remaining 18 electrons in pairs on atoms that do not already have a full octet, starting with the most electronegative atom. And which is the most electronegative atom, boron or chlorine? Chlorine, yeah. So 1, or 2 rather, and I always put them on in pairs. Does anybody know why? Why do I do pairs instead of single electrons? Why do I do pairs instead of single electrons? What do you think? Have you ever heard of something called a free radical? Free radicals are unpaired electrons. Free radicals are very destructive. Free radicals are very unstable. As such, they don't last very long in nature. Molecules will tend to adopt configurations that do not have free radicals in them. So, do always in pairs, never by one at a time. So, now you might be, at this point, we've already used up all our 18. So, if any atom is electron deficient, if it does not have enough electrons, we can share a pair by making an extra bond, right? In this case, you might be like, well, I could, if boron only has 6, I could share a pair of electrons from one of these chlorines, right? However, boron is exception to the octet rule. It only wants 6. It's one of those weird ones. So we don't actually have to share anything. Because boron is bonded to 3 chlorine atoms and it has no electrons on its no lone pairs of electrons, is this a polar or non-polar molecule? It's non-polar. And this goes back to Gen Chem 1, like the rules for polarity, if an atom is bonded to all the same outer atoms and there's no lone pairs, it's non-polar. If it's bonded to all the same outer atoms and there is one or more lone pairs, it will be polar unless the lone pairs are in opposite positions. Okay, so this one is not the answer. It can't have dipole-dipole attractions if it's not polar. Carbon dioxide, I'm going to go ahead and speed through a little bit. Carbon dioxide is C double bond O, double bond O. If you drew the Lewis structure, it looks something like this. Central atom, no lone pairs. Bonded to the same outer atoms. Is that polar or non-polar? Non-polar. What about arsenic trihydride? Well, AS has how many valence electrons?
5.
5. And each of the hydrogens has 1. So that gives you a total of 8 valence electrons. And probably separate this somehow. Okay. Now arsenic trihydride. So I'll put the arsenic over here. I'll draw a skeleton structure. Arsenic attached to 3 hydrogens. So in this case, is this polar or non-polar? It's polar because it has a lone pair, right? So that would mean this has the dipole-dipole. Now, if you started with XCF4, one of the things you notice with XCF4 is that it's 8 plus 4 times 7, because the valence electrons for xenon is 8, it's a noble gas, and for fluorine it's 7. That's 28 plus 8, which is 36. And then if you drew the Lewis structure, Xe, XeF4, we've lost 8. That would put us down to 28. And then you place the remaining electrons in pairs, so 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Well, that's 24. We can't put any more on the fluorine, so now we have to put them on the central atom, so 26, 28. So in this case, what we end up having to do is cancel, or rather, what we end up having to do is look at what the molecular geometry is. What's the molecular geometry when you have 6 lone pairs and 2 lone pairs and 6 total domains? Square planar, which means these lone pairs are in opposite positions, one above, one below, right? That means they cancel out, which means this is a polar or non-polar molecule? Non-polar molecule. So this is non-polar as well. So the answer is ASH3. That one's kind of a wicked one because it does really require you to kind of do your different Lewis structures and to know all those principles of intermolecular forces. Okay.
Can we do 3 and 4?
3 and 4, sure. Is it okay if I erase all this junk up here? Okay. Erase. Ah! Well, I'll erase some of it. Erase whatever's easy. Ah, bye. Okay. Okay, now it says, which of the following have the lowest boiling point? So the lowest boiling point means that it has the weakest or strongest intermolecular forces. Weakest, very good. So the lowest boiling point, weakest intermolecular forces. Of these, let's assign what the intermolecular forces are. So what would you say this one is? HCl. That's dipole-dipole. And water? Yeah. Ah. H bonding. And what about pH3? That's dipole-dipole. And what about SiH4? Yeah, so there's the dispersion. And what about H2S? Dipole-dipole. All right. So you look at all of these. Some of these obviously are going to have bigger boiling points. I mean, if you look at the size of them, chlorine is on the same level as phosphorus, and that's on the same level as silicon, same level as sulfur. Water is kind of off on its own, but water also happens to have, water's a little bit lighter, but water also happens to have the strongest intermolecular force, which is hydrogen bonding. Now here's the deal. It is possible, because dispersion forces stack, that if you have really, really high dispersion forces, you could actually be stronger than hydrogen bonding. But in order to have very high dispersion forces, you need a very large, a very heavy, and a very long molecule, okay? So in this case, none of these molecules are particularly more heavy than any of the others, right? So the only thing you're comparing really then is the type of intermolecular forces, and that would be dispersion would be the weakest, and therefore that's why it would have the lowest boiling point, presumably. All right, number 4, the following, which has the highest boiling point. So once again, if we're looking at this in terms of the mass, the masses of these are pretty similar. This is 28. The CH3, CH2OH, that's going to be closer to 40. This one's also going to be close to 40. C2H6 is going to be smaller. F2 is going to be about 40. I mean, but if we look at, so we want to look at two things, the relative sizes, and most times they're about the same. They're asking you to compare apples to apples. But sometimes they're asking you for, but oftentimes they're asking you to check for intermolecular forces. So what type of intermolecular forces would be present with N2? Dispersion, because it's nonpolar, right? And with this one, ethanol, hydrogen bonding, exactly, because it has an OH. If it has an NH, an OH, or an FH, it's hydrogen bonding. And what about this one? H bonding as well. And what about this one? Dispersion. And then the last one, also dispersion. So the two that have the strongest are B and C. Now, which one would make it stronger than the other? Or which one would be stronger than the other and why, rather? This one? Any?
Oh, wait, no, never mind.
Okay.
Never mind.
Okay. So which one of these is larger, B or C? Say B? B is actually not stronger. C is stronger. And there's two reasons for this. One, C has 2 instances of hydrogen bonding instead of 1. And C is also heavier, so it has stronger dispersion forces as well. Because remember, all molecules have dispersion forces. All molecules have dispersion forces. And in the case of C, this has it has 2 instances of hydrogen bonding, and it also has stronger dispersion forces. Both of those would give it a higher boiling point, much higher than ethanol. In fact, the name of this compound is called ethylene glycol, and ethylene glycol is used in antifreeze. All right, cool. Next. Should we keep going in order, or do you have one we skip ahead?
Oh.
11? Sure. It says, which substance has the strongest intermolecular forces? Now, intermolecular forces, one of the ways you can tell is by the heat of vaporization. If the attractions between particles are stronger, will it require more energy or less energy to separate them? More energy. So which one of these is going to be which one of these is going to have the strongest intermolecular forces? A. The A2X, the EY3, none of that really actually matters. What matters is the heat of vaporization. Try that again. All right, next. What should we do next?
9.
9? Okay. The enthalpy change for converting 10 grams of ice at negative 25 degrees Celsius to water at 80 degrees Celsius is blank kilojoules. And it gives you the specific heats of ice, water, and steam, as well as their heat of fusion and heat of vaporization. So the easiest thing to do here is, so the easiest thing to do here is to go ahead and draw a heating curve. Okay. Here's the temperature. Here's the heat added. Okay. You start out as a block of ice. Increase the temperature until it starts melting. When it's all melted, it heats up again. And then it starts boiling. Now in this case, it wants to go from negative 25 degrees Celsius. So let's say this is a negative 25 where we're starting. 25 degrees Celsius. And we're going to go up to 80 degrees Celsius water. Well, once we get to 0 degrees Celsius, what happens? Yeah, it melts. And then it heats up until we get to about 80 degrees Celsius right here. So this tells us that we're actually going to have 3 processes and therefore 3 calculations we're going to need to do. So the first, we warm up the ice, then we melt the ice, and then we warm up the melted ice or the warm of the water up to 80 degrees Celsius. So for that first one, There's really two equations that we use for this problem. There's Q. The heat transferred is equal to the mass times the specific heat times the change in temperature. And there's also Q is equal to the number of moles times the heat of the molar heat of fusion. Or you could say heat of vaporization if you're vaporizing it, but fusion refers to either melting or freezing. Okay, so in this case, we're going to go ahead and calculate this. For the first thing, for the first step, number 1, number 2, number 3. Number 1, the temperature is changing, so which equation are we going to use? Yeah, Q is equal to MC delta T. So the mass here is going to be, gosh, I wish I had more room. Oh, here, I'll do it down here. So Q1, I'll call it. The mass is 10 grams, right? And I should include my 10.0 with sig bigs or whatever. I'm just being lazy, sorry. And then the specific heat, in this case, is which one am I going to use? 2.09, because it's ice right now. And that's going to be joules per gram degrees Celsius. And then the temperature change is going to be the final change minus the initial. What's the final change? What's the final temperature here? 0, not 80, because I'm only looking for the final temperature of the first segment, segment 1. So 0 degrees Celsius minus the initial, which was negative 25. And when I subtract the negative, I turn it positive. So 10 times 2.09 times positive 25, that's going to give me what? 522.5? I'm going to trust you. I'll just do 523 because I only have 3 sig figs, and it's joules. Now, let's do Q2. Now, Q2 requires me to use which equation? Second one. Now, I don't actually have the moles of ice. I have 10 grams. So I'm actually going to go ahead and do this. I'll take my 10 grams water. And I will go ahead and convert the 10 grams to moles by using the molar mass of water, which is about 18 grams. 18.0 grams of water is equal to 1 mole of water. So that's my moles. And then I just have to multiply that times my heat of fusion, which for water is 6.01 kilojoules per mole. And what does that give me? 3.34 kilojoules, right? Now, I have to solve for Q3. Which equation am I going to use for that one? Uh-huh. So once again, I still have my 10 grams. And I'll use which specific heat? No. 4.18. It's the one of liquid water, right?
Yeah.
So be careful. 4.18 joules per gram degree Celsius. And it's final minus initial, so the final temperature is 80. And the initial is 0. 80 degrees minus 0 degrees And that's going to give me what? 3,344. I'm going to trust you. But notice that the unit has to be joules, doesn't it? Notice that unit has to be joules. So if it's joules, and I want the final answer, it's asking me for my final answer in what? Kilojoules. So I have to convert all these to kilojoules before I can add them up, right? One is already in kilojoules. So I'll just convert the others to kilojoules and then add them up. And if I do that, what do I get? Yep. Because this will be like 0.523. This will be 3.344. Add those all up, and it's going to give you about 7.21. That was a pain. How dare you make me do that one? No, you're fine. All right. What's next? Now this was all. That was all for question 9. That was all for question 9. Okay. What would you like to go through next?
Nineteen.
19, sure. Number 19. Calculate the mole fraction of phosphoric acid in a 25.4% by mass aqueous solution. So when converting these different types of units of concentration, the easiest thing to do is to write the definition of each of them and then kind of work your way around it from there. In this case, mole fraction, I'll write down here. We're doing this problem, 19. Mole fraction is listed as the moles of a particular substance A divided by the total number of moles in the solution. That is the mole fraction of A. Now in this case, I'm given percent by mass, and it's an aqueous solution. So percent by mass, percent means parts per how much? Percent. Parts per 100. So basically 25.4% can be written 25.4 grams of phosphoric acid over 100 grams of solution. Now, if I want to do the mole fraction of phosphoric acid, I have to calculate the moles of phosphoric acid. That's pretty easy to do because I already have the grams, right? But I also have to calculate the moles of everything else. What is the everything else in this case? It's an aqueous solution, so water. How much water do we have? Yeah, 74.6, because if you have 100 grams total of solution and 25.4 of it is the phosphoric acid, 74.6 of the grams is water. So let's go ahead and calculate the moles of water using the molar mass. Water's molar mass is about 18, or if you're really nerdy, you can use 18.02. You used 18.02, didn't you? I did too, it's okay. And then we can do the same thing for the phosphoric acid. 25.4. H3PO4. Now, let's see if you can calculate it on paper faster than I can in my head. .98. .00. That's right. What?
You said I used 97.99.
Oh, did you?
Yeah.
Yeah, that's actually okay because you probably did 1.008 for the hydrogen, right?
Yeah.
Yeah.
15.99 for the oxygen.
Oh, okay, okay. Well, then fine. You beat me in precision. H3PO4. That's 1 mole. So then all we have to do is multiply everything on top and divide by everything on bottom. How many moles of water did we get? 2.13? Oh, 4.13. 4.14, very good. And how many moles of phosphoric acid do we get? 0.259. So then all we have to do is take our 0.259, which is our moles of interest, moles of phosphoric acid, and divide by the added total of 4.14 plus 2.259. And that gives us what? Mm-hmm. 0.0589.
Did you multiply something for that?
Wait, what?
I did that wrong at first. I multiplied. Adding that.
Okay. Yeah, and notice if you had forgotten to add the 0.259 to the denominator, you would have gotten 0.0626. So you would have gotten one of the other answers, and you would have been like, oh, I did this right. We're like, no, you didn't. See how evil that is? They figure out how many ways you could mess up. They give you the moles of water, the moles of the phosphoric acid, and it's trying every which way to confuse you, like giving you possible correct answers or things that you could think that were correct answers but aren't. By the way, on the for my online viewers, are you guys hearing me okay? You can give a thumbs up if you want. That yeah, let's do 18. It says calculate the molarity of a 25.4% by mass solution of phosphoric acid. Molality. Okay. So actually, this is even easier. All you have to do is start with the same thing that we did last time. Remember how we started out with this? We do the same thing for this one up here. We're going to our 25.4 grams of phosphoric acid, H3PO4, and that's the percent by mass means that's per 100 grams of solution. Now, we already know that 25.4 grams of H3PO4 per what we did over here is 0.259 moles. And because I'm lazy, I'm not going to repeat that calculation. However, molality, remember, we also want to start with the definition of what we're looking for. Molality is moles of solute over what? Yeah, over what of solvent?
kg.
Kilograms of solvent. Very good.
I can't remember the
So kilograms of solvent, not solution, solvent. So we know that we have 25.4 grams of H3PO4, but how many grams of solvent do we have? 74.6. That's how many grams of solvent. Our solvent is water in this case, right? So I just need to convert this to kilograms. And 1,000 grams is equal to 1 kilogram. So that means this is going to be 0.0746 kilograms. So then all I have to do is divide the moles by my kilograms of solvent, and that will give me my molality. And what does that end up giving you? There you go. Da, 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 da. Ta-da. What? 20? All right. A solution is prepared by dissolving calcium chloride in water and diluting to 500 milliliters. If this solution contains 44 parts per million chloride ions, the concentration of calcium ions is what? Now, those calcium chloride, this one, it looks like you might have to do all sorts of crazy calculations, but you really don't. All you need to know is the formula, the chemical formula of calcium chloride. Calcium is going to have what charge? Calcium as an ion has what charge? Positive 2. And chloride as an ion has what charge? -1. So what's the formula of calcium chloride? Yeah, CaCl2. In the absence of any other substances, there should be roughly how much calcium per how much chlorine? In terms of the number of atoms, there should be how many calcium atoms per chlorine atom? Be half the calcium, right? So if the chloride concentration is 44 ppm, the calcium should be 22. That one's an easy one if you know what to look for. But it does give you extra information which could convince you that you need to do all sorts of crazy calculation, which you don't. What next? Are there any that look particularly interesting to you?
Yeah, I also asked. I didn't know what 17?
Thanks. No, we can't go backwards. You already jumped past it. Too late. No, I'm just kidding.
23?
No, just kidding. 17 is fine. Said 17? Okay. It says the concentration of CO2 in a soft drink bottled with a partial pressure of CO2 of 4 atm over the liquid is 1.2 times 10 to the negative 1 molar. The Henry's law constant for CO2 at this temperature is what? So in this case, this is just about knowing the Henry's law, or Henry's law. Henry's law basically states that the solubility of a gas is equal to some constant, some Henry's law constant, K, KH, times the pressure above, the partial pressure of the gas above it, the pressure of that gas. So it's actually a really simple relationship, which unfortunately you have to memorize. So solubility of the gas, the solubility is given the concentration. And then the pressure of the gas is given. So you just have to solve for Henry's law constant. What would it be? What'd you say? 3.0 times, yep, I think that's about right. There you go.
So you don't need the temperature.
No, because the Henry's law constant is specific to the temperature. So it's only, in fact, that's why it says the Henry's law constant for CO2 at this temperature. If you change the temperature, you change the Henry's law constant. Sorry. What next? Did you say 23?
That was also another Henry's law one.
Oh, okay.
You said we could go back, so I was like, okay, so 23?
Okay. I mean, do you want to do 23 or do you feel like you're fine with that? Okay. What did you say? Okay. So once again, Henry's law constant for helium gas in water is 30 degrees is 3.70 times 10 to the negative 4th molarity per atm. When the partial pressure of helium above a sample of water is 0.650 atm, the concentration of helium in the water is what? So once again, this is solubility. You can read solubility of the gas as concentration is equal to the Henry's law constant times the pressure, partial pressure of the gas above. Okay, so this is the Henry's law constant, KH. And this is the partial pressure. So this is even easier than the other one. All you have to do is multiply them. Which means the answer is, yep. Okay. What else can I help you with? $31. Oh, I'm sorry. Okay. The reaction is a first order reaction at 230.3 degrees Celsius. The rate constant is 6.29 times 10 to the negative 4 seconds to the negative 1. If the concentration of N-methyl, whatever it is, methyl cyanide is 1.00 times 10 to the negative 3rd initially, then what is it after 1,000 seconds? So whenever you have changing concentration, you're probably going to end up needing, I mean, you could use an ice chart, but in this case, it wouldn't really make sense to do it because And whenever something involves changing concentration with respect to time, you're really dealing with the integrated rate law. And I don't know if your professor is going to give you the integrated rate law, but if they don't, the integrated rate law that you have to memorize is as follows. Ln of the concentration of a substance at time t is equal to negative kT, where k is the equilibrium constant, plus the Ln of the concentration initially. Okay. So in this case, it wants to know what the concentration is after 1,000 seconds. So which one of these variables are you solving for? You're talking about, yeah, you're solving for A at time t, not the Ln of A at time t, but A at time t. So the nice thing is you can just go ahead and plug in the numbers and solve for this. Negative kT means it's negative 6.29 times 10 to the negative 4th seconds to the negative 1 times 1,000 seconds plus the natural log of A initial, the initial concentration, which is and that's equal to the Ln of A at time t. Now, rather than just trying to solve this all in one swoop and raising e to the both sides and then try to put this whole thing in e, I would recommend first calculating what this number is and then taking e and raising it to it. So what does that give you? You have 1,000 times negative 6.29 times 10 to the negative 4th. It's going to become negative 0.629. And then you're going to have the ln of 1 times 10 to the negative 3rd, which is, what did you say? Negative 6.91. And this is going to be a unitless quantity.
Oh. Wait, hold on. I thought you were just asking for the.
So that's not the final answer, yeah.
No, it would be negative 7.54.
Oh,
I just took the natural log. I thought that's what you were asking for. The total is negative 7.54.
Negative 7.54.
Mm-hmm.
And then you just raise e to the both sides. So A at time t is going to be e to the negative 7.54, which is what?
I got 8.
You got 8? All right. I'll trust you then. 3 times 10 to the negative 4th. Now, from a logical perspective, which two answers could automatically have been ruled out? From a logical perspective, which two answers could have automatically have been ruled out? Say, for example, if you let's say you didn't know how to do this problem, okay? let's say you didn't remember the first order integrated rate law. You're stuck, okay? But looking at this problem, you see what it gives you. Which two answers obviously could not be the case? After something reacts, do you ever have more of the reactants? No. So which two answers could obviously be ruled out? That's okay. Because it's important to do these little logic things in your head, because if you're running low on time, you don't have enough time to work out a problem, but you have maybe a few seconds to get a few pieces of information to go ahead and make an educated guess. In this case, the reactant starts out as 1 times 10 to the negative third. So if you are going to go, it has to go down from there, right? So the ones that you could almost certainly reject would be which ones? B and C, because B and C have more than you start with, and that wouldn't happen in a case where you're reactant, you know. Also, another thing to notice is you could probably rule out D as well, because D is such a significant drop from this. I mean, as with first order reactions and second order reactions, as the reaction proceeds, as the reaction proceeds, it actually goes down, right? It slows down. So the less reactant there is, the slower it reacts. So it probably wouldn't drop all the way down to 1 times 10 to the negative 6. So you'd be left with two answers, 2.34 times 10 to the negative 4th, or 5.33 times 10 to the negative 4th, and at least then you have a 50-50 shot. Okay. Not that I want you guessing, but you know. Okay. What else can I help you with? Any other questions? I mean, online people want anything? Let me know if you can type in the chat. If you don't want to talk, that's totally cool. Just let me know what questions you might want to check out. $33 and $35. Let's do it. Okay. So 33, it says the rate constant of a first order process that has a half-life of 225 seconds is blank. Now, this doesn't give you a whole lot of information to start with. I don't know, did your professor indicate what formulas he would give you at all, if any?
None.
None, okay. All right, so this is the half-life is the only, you can derive the half-life from the integrated rate law, but it's also convenient to have at least this first order integrated rate law half-life memorized, because the half-life equation is very simple. It's T 1/2. That does not mean you multiply it by 1/2. That's a subscript that tells you it's half-life. So T 1/2 is equal to ln of 2 over K. ln of 2 is 0.693, but it's actually more accurately ln of 2.
He told us that since our K was negative, that we would be taking the natural log of 0.5. The equation he gave us had a negative K.
You said what about K?
So it was like natural log of 0.5 equals negative K times T.
No. Absolutely not.
Because it was, because we were doing a question like this.
He might have been going over an example problem or something like that, but like I can tell you the equation for half-life for a first order reaction is ln of 2 over K.
Okay.
Yeah. And if you did not know or you could not remember half-life, another easy way to just determine what the half-life is to go ahead and recognize that if you have the integrated rate law, if you remembered that, and I'd recommend memorizing the linear form of the integrated rate laws. So at the half-life, in other words, if this is T1/2 or the half-life, how much remains of the original sample? Hint, hint, why is it called half-life? Half of it remains, right? So half of the original sample remains, which means this A at time t is simply half of what the original one was. It's 1/2 A initial. Okay. So then if I subtract, if I add KT to both, KT 1/2 to both sides, and I subtract the ln of A naught, I get KT 1/2, the half-life, is equal to the ln of A initial minus 1/2, or rather ln of 1/2 A initial. Now, if you remember your rules for logarithms, if I take the one logarithm minus another logarithm, I can write that as the logarithm of the first one over the second one. And that's equal to KT 1/2. Now, of course, the A naught cancels out and is basically the log of 1 over 1/2. Well, 1 divided by 1/2 is 2, right? Divide by a fraction and multiply by the reciprocal. So this becomes ln of 2. And then if you want to solve for T 1/2, you just divide both sides by K, and that gives you this guy, ln of 2 over K. That's equal to the half-life. So now, since it gives us the half-life, 225 seconds, all I have to do to find the rate constant is to multiply both sides by the rate constant to give me the KT 1/2 is equal to the ln of 2. And then I divide both sides by T 1/2. And that basically is going to give me just a little bit of algebra. It's going to give me ln of 2 divided by the half-life is equal to the rate constant, which in this case is the ln of 2 divided by 225. Does that make sense? Any questions on that? Okay. Well, we still have a little bit of time left. What would you like to go over? Which one?
35.
35. In the Arrhenius equation, blank is the frequency factor. Well, that's just a definition thing. First of all, what's E of A? EA, what's that? Activation energy. What's R? The ideal gas constant. And what's T? Temperature. And what's K? The rate constant. So that only leaves you with one that's a frequency factor. A. And E is just the inverse of natural log. By the way, this is one of the reasons why I have up on my website, or up on the Canvas Learning Commons page, if you go to Chemistry 1412 under concept reviews, for 1412, if you click on the chapter like chemical kinetics, it actually has all of the equations and the definitions of each. It explains what each thing means. So like, for example, rate is equal to K A to the M B to the N. K is the rate constant, M is the order of reaction with respect to A, N is the order of reaction with respect to B, and A and B are concentrations of reactants A and B respectively. So, well, that's like, okay, yeah, well, duh. But for something like this is actually helpful because A is a constant known as the frequency factor, and E is a constant, or activation, and E is activation energy, R is the ideal gas law constant. It gives the different values. So studying with one of these on hand, the summaries, chapter summaries, would be really helpful. I also have, in addition to the web version, there's also PDF versions that you can download and print. Plus, if you ask us, we will print them in here for you for free. So that is an added perk to coming into the Science Learning Center in person. Yeah. So we have the PDF version as well. Cool. Now where am I? Oh, there we go. Okay. Now what do we want? Ah, that's not the answer. Taking all callers. $27? Okay. For those of you watching online, you missed the opportunity of seeing me dance. You didn't miss much. Nitrogen dioxide decomposes to nitric oxide and oxygen via the reaction 2NO2. There we go. 2NO2 goes to form 2NO and O2. In a particular experiment, nitrogen dioxide drops from 0.01 to 0.065 in 100 seconds. The rate of disappearance for this is blank. So the rate of disappearance of something is simply the absolute value of the change in NO2 over the change in time. That would be the rate of disappearance. Now, if it was asking you for the rate of the reaction, and actually do the absolute value of this for the rate of disappearance, but I'll write it's rate of disappearance. Rate of disappearance. Bam. Oh, equals. There. If you were wanting the rate of the actual reaction, then you would actually express it as if it was it'd be the negative 1/2 times the concentration of, or the change in the concentration of NO2 over the change in time. And the reason why you put the 1/2 is so that when you express the rate of reaction, you always do so in terms of the fraction of the coefficient. That's why you put everything on the same level, because if it's 2 NO2s for every 1 oxygen, then NO2 is going to be reacting or changing twice as fast as oxygen, right? And you want to represent things all at the rate of reactions, they all change at the same pace. So you always do it in terms of the fraction of the coefficient. And this term right here, the one in parentheses, is your rate of change of NO2. Rate of disappearance is just the absolute value of that. You cannot have a negative rate of a reaction, and you cannot have a negative rate of disappearance, or a negative rate of appearance for that matter. If it asked you for the rate of change, what is the rate of change in the concentration of NO2? That could be negative. All right, in this case though, we're just looking for this. Whoops. We're looking for that. So what does that give you? So you take your final concentration, which would be this, minus your initial concentration, which would be this. And then you take that answer and divide it by the change in time, which is 100. And remember, we're not going to multiply by 1/2, so this is just going to be what? Mm-hmm. That's right. Makes sense? We all good? Okay. What's next? One of the reasons I don't really care for some of these rate law problems is because some of them are really just it really just boils down to semantics, like how they word the question. And so you have to kind of be really sharp when picking up the verbal cues to determine whether or not something should get a negative sign and whether or not something should not get a negative sign. But if it helps you to remember this, remember it. Rate is always positive, and rate constants are always positive. Rate constants are always positive, and rate is always positive. Now, the integrated rate laws may have a negative in front of the rate constant, but the value of the rate constant itself, K, is always a positive value. Because a negative value for the rate constant would mean that the reaction's going backwards. So we never talk about reactions in terms of them going backwards. Okay. Next. 14 minutes left. Yes. 26. The osmotic pressure of a solution can be formed by dissolving 25 milligrams of aspirin in 0.250 liters of water is blank ATM. So in this case, this calls for us to use the osmotic pressure equation, which is actually, believe it or not, the same as the ideal gas law equation. Because molarity is just moles per liter, right? If we wrote osmotic pressure with a P instead of a pi, this would be N over V times RT. It's the ideal gas law equation, back from the dead. Anyway, so ideal gas law equation returns from the dead to confront you as osmotic pressure. All right, so to solve for the osmotic pressure, all we have to do is calculate the molarity and then use RT. Since it's an ATM, what is the value of R going to have to be? Yeah, very good. 0.08206 liter ATM per Kelvin mole. And then our temperature is what? Yes, it's 273 plus 25, so yep. It'd be 298. We can just leave it as 298. You don't have to use the 1.5. And besides, it wouldn't be appropriate to do so because 25 is only 2 sig figs, which means we don't know if this is 26 or 24. Could be either. So we cannot pretend to a precision we do not possess. I'm sure that sounds like a movie quote, which it may be. All right. So next, molarity. We have to calculate the moles and we have to calculate the liters. Well, we have the liters, we don't have the moles. So 25.0. Fortunately, we are given the formula of aspirin, 25.0 milligrams. And I'll convert my milligrams to grams. 1 milligram is 0.001 grams. Milli means 1/1000. You could also say 1,000 milligrams is equal to 1 gram. Whatever floats your boat. And C9, H8O4. So 168. Oh wait, no. What is it?
It's 180.159.
180.159. Yep. I'll trust you. I was trying to do it in my head, but I was too slow. So that's grams per 1 mole. So this is going to be really, really tiny. So how many moles is that? Preferably in scientific notation. What'd you say? Okay, 1.39 times 10 to the negative 4. So we can simply take that moles of aspirin divided by the liters, 0.250, and then multiply it by R and T. And if we do so, what do we get? Okay. I will trust you. I don't know why it wouldn't be that. Okay. And then I'm going to choose to not trust you by checking the answer key. 26, C. Okay. Well done. Okay. Oh, it's not 1.14 times 10 to the negative 3rd. You lied to me. We're going to have to double check our calculations. Double check my calculaciones. Okay. It's C, right?
Yeah, 0.0136.
Yep.
0.321.
Somebody told me something else. That's all I'm going to say. I'm pretty sure somebody told me something else. Wink. Okay. Did y'all see where you made your mistake, or? I don't remember who actually said. With everybody wearing masks, I can't tell who's talking half the time. So, my apologies. All right, cool. Next, I think we can do one more. What do you think? Let's do it.
Question.
Honestly, whatever. Right now I'm getting like
Overwhelmed? I'm sorry.
No, it's okay. It's just my fault. Like, I don't know. It's not an excuse, but I just work a lot, so I haven't had the time to like.
Oh, yeah.
And stuff. So right now I'm just gonna like.
Yeah, I understand. I hope I'm not going through it too fast, am I? Okay. Yes.
28.
28. Which one of the following is not a valid expression for the rate of reaction below? So remember when I said the rate of reaction can be expressed in terms of the fraction of the coefficient times the either rate of appearance or disappearance? So if we were to write the rate of the reaction, we could write 4 expressions here. Because rate of reaction has to be positive, and because the change in the concentration of any reactant is always going to be what? Our reactant's going to go up or down? As the reaction proceeds, does the amount of reactants increase or decrease? Decrease, right? So the change in the concentration of reactants is always going to be what? Positive or negative? Negative. So if I need a positive rate of reaction, then I'm going to have to add an extra negative sign to counteract, right? So, and I'm also going to have to do a fraction of the coefficient. So I have this 1/4, negative 1/4 change in concentration of time over 1/4, negative 1/4 change concentration of the reactant over time, of NH3 over time. Or I could have negative 1/7 the change in concentration of O2 over time. Or I could have positive, products. There's going to be more products later on than there are to start with, right? So for the products, I can say I have a positive 1/4 change in concentration of NO2. Over change of time. And positive 1/6 change in the concentration of H2O. In this case, yes, they are. I love problems like that because they're evil.
Because it makes you work it all out. And
Yeah.
Oh, it's all of that. Thanks.
Shame on me. I used to give, when I was teaching, I used to give pretty evil tests. Like they'd have lots of really hard problems. It wasn't like stupid things like stupid trick wording and such or whatever, but it was questions that were complex and difficult. But I would also always give my students unlimited time to finish the test, and I would also give them, I would grade on a curve. Yeah. Okay. Actually, I might have. I think I might have. All right. So, what's next? I guess I can do one more. Since it's 6:27, we're supposed to go to 6:30, and I was a few minutes late to start. Sorry. One last hurrah.
I can choose.
5. Number 5?
Mhm.
Whoa, we're going back to the beginning.
Sorry.
Number 5, it says, what is the prominent intermolecular force of CBr4? A. Okay, what next? No, I was kidding.
I had a lot of trouble with chapter 11, so that's why I'm asking all of
No, that's totally fine. No, CBr4, once again, this is one where you kind of have to draw the Lewis structure. Carbon has 4 valence electrons. Bromine has 7 valence electrons. So 7 times 4 is 28, plus 4 is 32. So that's the total number of valence electrons. Then you draw your skeleton structure. Now, at this point, you may already recognize, since it's CBr4, carbon is bonded to 4 bromines. You really don't even have to continue with the Lewis structure because carbon is bonded to 4 different groups. Carbon already has a full octet, right? And carbon does not have any lone pairs, right? And it's bonded to all the same outer atoms. So by definition, that's going to be polar or nonpolar? Nonpolar. And nonpolar means that the type of force is going to be dispersion. Yes?
So if the central atom has like all the bonds, but there's like one ionic there, or one.
So let's say this was bromine, and this was like fluorine.
Yeah.
Then it'll be polar. If even one of them is different, then it's probably going to be polar.
What if two are different? Like there's like 2 bromine.
Still polar.
Okay.
Because you have to remember, this is not accurate depiction spatially. This looks like it would be a square planar, but in actuality, this is a tetrahedron. And in the tetrahedron, 2 of these are always going to be closer to one side, and 2 of them are always going to be closer to the other. So 2 of them are chlorines and 2 of them are hydrogens. The chlorines will be more negative on this side, will be more positive on this side. Okay, cool. Well, thank you for coming. It was fun, and for me at least. And I wish you the best in your test. Please feel free to come by and study with us more if you wish. If you want to do more studying prior to your test, and we'll call it there.